For investigation 1B, which is called air patterns, which is kind of an innocuous term for what it is that we're going to be discussing here in this video and in the investigation. This investigation is really going to focus on the pressure of the atmosphere at the Earth's surface, how pressure varies across the Earth's surface, and what that ultimately is going to mean in terms of our winds. And we're going to spend a lot of time talking about pressure in our class because it's ultimately going to be these variations in pressure across space, what we refer to as a pressure gradient, but it's going to be pressure gradients that really in our class we're going to use to kind of describe wind patterns in terms of both direction, circulation, and speed. So in that context, this is a fairly important investigation. I don't think it's a terribly difficult investigation, but it is important. So why don't we get started and we'll get right to it with our slideshow here. All right, so air patterns. And so what I want to do, I'm going to bring up figure 1B1, but I'm not going to do anything with it for a little bit here. And what I want to do instead is just talk about pressure for a few minutes, because pressure is really important. We all know the word, we all have a sense of what it means, but in scientific terms, a lot of us don't. We don't really quite understand how physicists use this term pressure. For our purposes in this class, and it's true, pressure is a measure of weight, and for our purposes, we're going to be talking about the weight of the atmosphere. Now, when we talk about weight, when we jump on a scale, or maybe step gently on a scale, maybe more like it, we're measuring our weight in total weight, and you can think of that as pounds. Now, when we're talking about the weight at the Earth's surface, if we were measuring the weight of the atmosphere at a certain location, we'd be looking at it in terms of pounds per square inch, but we don't use pounds per square inch in our class. Instead, we use millibars. As I said in the Investigation 1A video, millibars is derived or comes from a metric for Pascal, the MKS system for the measure of pressure or weight. So we're going to use millibars in our class, but I just want to make it clear that it's still a measure of weight. Now, an atmosphere, the actual technical definition of an atmosphere is a unit measure of weight. And an atmosphere in millibars equals 1,013.25. So an atmosphere weighs 1,013.25, which illustrates what I also said in the 1A video, which is that at the Earth's surface, at sea level pressure varies between about 950 millibars on the low end to 1,050 millibars on the high end, and 1,000 is right there in the middle. So 1,013.25 is the precise measurement of what the unit of an atmosphere is. An atmosphere also weighs 14.5 pounds per square inch. So that's something that we can understand a little bit more. So imagine that you're standing outside right now, or just sitting wherever it is you are, and because the weight of the atmosphere is roughly an atmosphere within a couple of millibars, then the atmosphere is actually pressing on you 14.5 pounds per square inch. Now, you don't feel it because, in fact, we are engineered to be pushing outward 14.5 pounds per square inch so that everything feels nice and normal. But if the weight of our atmosphere was 2 atmospheres, and we put an extra 14.5 pounds per square inch on our body, we'd feel it. Now, the final measure, and we're not going to really use it in our class, is what we measure with an actual barometer. And when we use a barometer, we use a measure of inches of mercury in a barometer. And we're not going to really talk about barometers and how they're constructed, mostly because mercury is a neurotoxin, and that's what we actually use in old school barometers. So we really don't use barometers very much anymore, but you may still hear barometric pressure thrown around in the language. So a measure of an atmosphere in barometric pressure is 29.92 inches of mercury. So I'm giving you kind of a complete description, but in our class, we're going to be millibar driven the entire way. Now, what we have here in figure 1B1 is a map with pressures on the eastern United States. So these are pressures that are measured with ASOS, and they're reported, and we put these on a map. And what you'll see in the northeast corner is that a couple of isobars have been drawn. Now remember that an isobar is a line of equal pressure. So everywhere on this isobar, the pressure is exactly 1,004 millibars. Everywhere on the isobar next here to the south and west, everywhere on this isobar, the pressure is exactly 1,008 millibars. Now, we like to draw isolines in meteorology, in atmospheric sciences, because for starters, isolines help us to organize our data. When we draw an isoline, so everywhere on the isoline we have the same value, what the isoline does for us for the get-go is it separates higher values on one side from lower values on the other. And that's a really nice first general cut at what an isoline does. But what we'll see when we draw isolines in our class is that you'll see the isolines tend to show us patterns. And so we can actually see how pressure is varying across space. All right, so we're going to be drawing isolines in our class. We're not going to really do it a whole lot. We're just going to do it once or twice in our class. If you move forward beyond this class and you take Geography 2130, which is meteorology, you'll draw a lot more isolines than we're drawing here in Geography 1260. So what the AMS does, it provides a nice set of rules to get you going on drawing isobars on this map. So let's go through the tips to drawing isobars, because they're all really important and they're all valuable and they're worth going through. So again, starting with what I said, always draw an isobar so the air pressure readings are greater on one side and less on the other. An isobar will always do that. If your isobar is not separating higher from lower, then you have not drawn your isobar correctly. So when positioning isobars, always assume a uniform pressure change between neighboring stations. So when we draw isobars in our class, we're always going to use the same values. So we're going to use a base of 1,000 millibars, and I'll show this in another slide. But we're going to use a base of 1,000 millibars, and we're going to go up and down in increments of 4 millibars. So it'll always be 1,000, 1,004, 8, 12, 16, 20, 24, and so on. 996, 992, 988, 984, and so on going down. Now we're only going to draw isobars that correspond to the range of values that we have on our map. So we're not going to draw all of them. We're just going to draw the ones that correspond. So you're going to want to figure out what the lowest value on the map is, what the highest value on the map is, and then you'll know which isobars you have to draw. Now, sometimes, like on this map where we have 1,004 millibars, we'll be lucky and we'll get an isobar that actually goes right through a station that has our exact number. But sometimes, even though we have to draw the 1,004, or in this case 1,008, there's no 1,008 on the map. So what we have to do is we have to interpolate between the values that we get, because we have to draw 1,008. The values that we use for our isobars are set. You can't just draw 1,009 or 1,007 because it works better for you. It's always these increments of 4 going up and down from 1,000. All right, so you can see here that when we don't get the exact value on our map, we have to interpolate. And that is what point B tells us. Assume uniform pressure change. And so basically, if you have 1,014 and 1,018, and you have to draw 1,016, you just split the difference. Okay, adjacent isobars tend to be shaped alike. They're not identical, but when you do get changes in shape between adjacent isobars, they tend not to be radical changes. So you can see that the shape of the 1,004 and 1,008 millibar isobars are similar, but not identical. Okay, you continue drawing isobars until you run out of data. All right, so for example, and I would not have drawn these isobars even as far out into the Atlantic Ocean and into Canada as this map does. So you just draw isobars where you have data. So you wouldn't draw an isobar all the way out here, like 500 miles off the coast of North Carolina. You would draw an isobar that just basically goes out a little bit into the Atlantic, and then you'd stop because we've run out of data. All right, so that's what you do with our data. You only draw isobars as far as you've got your data, and then you stop. All right, isobars never stop within a data field. That's true. So as long as you've got data, you keep drawing isobars. Also, isobars don't fork, so you don't get a fork in isobars, and they don't close. So the reason, or I should say cross, the reason isobars don't fork is because basically what you're doing is you're creating a middle ground between isobars that have the same value. So if you have to draw a second isobar with the same value, you do that, but you don't fork. Now when it comes to isobars crossing, you can't have isobars with different values crossing, because that would mean that where you have isobars crossing, at that cross point, you have a location that has two pressures at the same time. Like if 1,004 and 1,008 cross, that would mean at that location, the pressure is both 1,004 and 1,008. That's like saying that you weigh 116 and 140 pounds at the same time, and you don't. So they can't cross either. All right, and you don't skip isobar values. You have to actually go up in our sequence 4 at a time, from 1004 to 8 to 12 to 16, and so on. You don't just go from 1004 to 1012 and skip 1008. All right, so you have to keep going on these increments of 4 millibars, and you don't skip an isobar. And then finally, you always label your isobars. So when somebody is reading a map, when you read a map, you want to know what your isobar values are. So you can see here that 1004 and 1008 are labeled, and that way you're not just drawing and having to look at the data to guess what the actual isobar value is. All right, now what I've done here is I've taken a different example from the one that the AMS has given you in figure 1B1, because I want to show you basically how to draw these things without actually giving anything away from the current investigation. So here's an example that looks kind of similar. We have lower values in New England, and the values extend outward and increase outward. So what I'm going to do is just do a little bit of drawing. Now, first of all, here is our range of isobar values going up and down from 1,000 millibars in increments of 4. Now, again, you're not going to draw all of these, because what you'll see here is that the lowest value on this map is about 1,006 millibars. And the highest value, just taking a look, is about 1,034. So what you would do is you would start with 1,008, and you would keep going up in increments of 4 until you got to your highest value. It's 1,035. So basically, you'd start with 1,008, 12, 16, 20, and I'd be going up from this range. We'd still draw more, 1,024, 1,028, 1,032. So you can see our highest value is 1,035. So the isobar, the highest value that we would draw on this map would be 1,032. We wouldn't draw 1,036 because there's no 1,036 on this map. In fact, we would need a value greater than 1,036, like 1,037, so we could draw the 1,036 millibar isobar so that it would separate a lower value, like 1,035, from that higher value of 1,037. Okay, so again, our low value is 1,006. Now you can just put an L, indicating the lowest pressure, the lowest weight of the atmosphere right there. The highest value is 1,035. So you can put a high, indicating that the highest weight or the highest pressure of the atmosphere is right here in Kansas. And then here are the values in between. These are the isobars that you would draw on this particular map. Everything from 1,008 all the way up to 1,032. Now, what I'm going to do is I'm just going to draw a couple more of these to show you how it's done. Now, if I were drawing this live right now, I would actually just show you my cursor moving through. But I'm going to just show you this in segments. So here's our 1,000. This is going to be our 1,016 millibar isobar. Now, what you'll notice is that we only have one value of 1,016 on the map, and it's right here in Pennsylvania. Everywhere else, I'm basically interpolating between values that are less than 1,016 and greater than 1,016. And I'm only drawing the 1,016 millibar isobar where we have data. So I don't go any further beyond where we have data. And then I label the isobar. And you'll notice that the 1,016 millibar isobar has a shape that is similar to the 1,012 millibar isobar. It's not identical, but it's similar. Here's 1,020. Now we're lucky, we have a couple of 1,020s on the map. And I'm going to keep on drawing and out to sea, and we're done. Now notice we were very fortunate here. We have 1,020 sprinkled all the way across from Minnesota to the Outer Banks of North Carolina, so that this was a fairly easy one to draw, label it. Again, notice that the shape is different, but it's only evolving slowly from one isobar to the adjacent isobar. And I'll draw just the last one, which is our 1,032 millibar isobar, starting in Nebraska, going into northwest Missouri, and then into Arkansas and out. And you'll see that in the bottom here, in the southern part of this isobar, we don't have any 1,032s. So again, we're interpolating between values that are less than and greater than 1,032, and we're trying to split the difference accurately. In fact, right here between Missouri and Kansas, this actually probably could have gone a little bit further west than it did. But this gets the point for you. So you can see this is how you're going to draw your isobars. Now, whenever you draw isobars on a map, and this is particularly for those of you who may draw more than we do in our class, you don't want to start here in the middle. You want to start with the lowest or the highest pressure and then work your way outward from there. So if you start with the highest pressure, in this case 1032, then you would work your way down from there to 1028, 1024, and work your way down to 1008. Now in this case, because the 1008 millibar isobar is so small, I would start 1008 and then work my way out and upward 12, 16, 20, and so on. So that's how I would do it. But it's up to you. But I would start with the extreme and work outward from your extreme high or low. So look at the map, assess your values, find your range of isobars, and then start drawing. All right. What else do I have here? Oh, I guess I did do a little bit more. All right. So I did 1028. All right, I didn't do anything after that. So now what I want to do is I want to define pressure gradient. Pressure gradient is a measure of the rate at which pressure changes over distance. So if we just go back to our last map, you can see that pressure is changing over distance. So what the pressure gradient does is it basically allows us to calculate the rate at which this pressure is changing over distance. So delta P is change in pressure over delta D, change in distance. So the pressure gradient, again, is a measure of the change of pressure over distance. And the pressure gradient increases as the spacing between the isobars decreases. So here is a map from 2024. This is from January 8th of 2024. And so this is something that I'm just putting on. This is not from your investigation. But we have a really nice example of a fairly deep low pressure system that's located over New Mexico and the Panhandle of Texas, and then high pressure that's located over the Ohio Valley. So we basically have pressure that is changing from low to high. Now, if you take a look at the pressure gradient, basically when the isobars are packed together like we have right here and just outward from the center of the surface though, this basically means that this 4 millibar change in pressure is occurring over a relatively small distance. So change in pressure over distance is big. Pressure is changing rapidly over distance. Large pressure gradient. Now when we get closer to the center of the high, and let's just take a look between, this is 1024, 1028 millibar isobars right here, and you'll see that pressure over this distance is a 4 millibar change still, but it's occurring over a much bigger distance. So pressure is changing much more gradually. This is a small pressure gradient. So the closer the isobars are packed together, the larger the pressure gradient becomes. Now this is important because the magnitude or the size of the pressure gradient is proportional to the wind speed. So the closer the isobars are packed together, the faster the winds tend to be. And the further apart the isobars are from each other, the slower the wind tends to be. Now we've not really talked about station models or anything like that quite yet, but just know that where the pressure gradient is large right here, the winds are around 15 to 20 miles per hour. And in fact, if we had a denser network of observations showing here, I suspect that wind speeds would be much higher. If you take a look at these double circles right here in Alabama and Tennessee, this indicates that the winds are actually calm. There's no air movement at all. So where the pressure gradient is small, the winds tend to be much lighter. Where the pressure gradient is large, the winds tend to be much stronger. Now, the next thing we're going to talk about is wind circulations around centers of high and low pressure. And what the AMS is going to do here is it's going to provide a device called the hand twist model. And this is basically allowing you to use your hand to basically do hand motions to figure out the sense of the circulation clockwise, counterclockwise, in or out, and then up or down around centers of high and low pressure. Now, I'm not a big fan of memorization because I don't think memorization imparts any learning at all. And in fact, this device, the hand twist model, doesn't really explain why we get these circulations. It just tells you what they are. So it's a device that is helpful. In fact, I've never used it. I never heard of it when I actually learned this information, before the wheel was invented. But the fact of the matter is that this is something that you might just need to memorize in terms of counterclockwise, clockwise, in, out, up, down, around centers of high and low pressure. The AMS actually has created a nice little video on YouTube, and here is the link for it, so you can actually take a look at this little video. It's just 2 minutes long that explains the hand twist model and how you can use it to show the circulations both horizontally and vertically around centers of high and low pressure. And you're going to be asked some questions about these circulations in the investigation. Now, when it comes to low pressure, just know that after you do the hand twist model, you will find that the circulations are counterclockwise and in. I'll let you figure out this vertical part with the hand twist model in the video for yourself. With high pressure, it's the exact opposite, clockwise and out. Now again, if you don't want to do the hand twist model, most people actually find it quite useful, but if you don't actually find it useful and you just want to memorize what these circulations horizontally and vertically are, I'm giving you the horizontal here. Again, with low pressure, counterclockwise and swirling in, with high pressure, clockwise and swirling out. And again, you can look at the hand twist and get the vertical aspect for yourself. And again, there'll be some questions about that. All right, and I think that's everything I'm going to be saying about Investigation 1B. Again, remember that you can take the quiz on Canvas for Investigation 1B as many times as you like during the preview week and week 1 of our class, and I again encourage you to do it. But if you have any questions about any of the content in the investigation, by all means, feel free to post it to the discussion board. Ask me live on my office hours in Zoom. If you see a question on the discussion board and you know the answer to it, please, as a student, provide the response. It will absolutely help your participation grade. Okay, but that's it. That's all. I'm going to end this now. Post it on YouTube, and you'll get a chance to see it when it's all ready for you to see.